So let me tell you what the axioms or postulates were. And I keep switching between whether I call them axioms or postulates. In the original paper I wrote in 2001, I called them axioms, but then often people think of axioms as very mathematical um, statements, whereas what I really wanted was something that was more physical. So postulates might be a better term. So, here are the postulates. Well, the first one is to do with information. So if you have some file and you store it on a memory stick, or you store it on a hard drive, or you store it, back in the 1980s on a floppy disk, um, then all those different ways of storing it are really equivalent, and it doesn't matter because those different means of storage have the same properties. And you can turn that idea into an axiom. You can say that systems that have a given information carrying capacity have the same properties. Okay, so that's a statement you can make, and you can give that precise meaning. So that's one of the assumptions. Systems that have the same information carrying capacity have the same properties. It's true in classical information theory, and it's also true in quantum theory. The second and third axiom concern composite systems. So if I've got two systems, then I'm interested in the way they behave as a composite. So here's an example, again, thinking about memory sticks. If you have one memory stick that can store 8 gigabytes and another memory stick that can store 2 gigabytes, then together they can store 10 gigabytes. Okay, and it doesn't have to be that case. It could be that when you bring two memory sticks together, they somehow discover extra storage capacity that wasn't there before. But we take it as a postulate that that's not true. That when you have two memory sticks, the amount of information they store is the sum of those two, of the sum of the two memory storages for the two components. So there's that assumption, and then there's another assumption. So I call that assumption information locality. There's another assumption called tomographic locality, which is a very similar thing, that when you bring two systems together, the number of degrees of freedom for the composite system is just got from looking at the two systems separately. Okay, so it's a similar principle. And then there's just two more axioms. One of them is continuity. Okay, and this one works for quantum theory, and it doesn't work for classical probability theories. So the idea is that you have a system in a definite state, and I want to get it to some other definite state. And the axiom says that you can do that in a continuous reversible fashion. So I want to go from one pure state, one definite state, to another definite state. And I want to get there in a way that doesn't jump, but it's continuous. And I want to get there in a way which is reversible. So at any stage I can go back. And you can do that in a quantum system. The reason you can do that is because of superposition. So if I have a system in state A and it's not in state B, and then I can make it so it's a little bit in state B and a little bit less in state A. That's a quantum position, and I can slowly grow how much it's in state B versus state A, so I can go continuously from one to the other. In classical systems, if I have a system in one state and I want to get into the other state, then I just have to jump. I have to go from this state to the other. So in classical theories, you have to jump, whereas in quantum theory, you can go continuously. So this is a striking difference between the two theories. And then the final axiom is a simplicity axiom. So the fifth axiom is a simplicity axiom. It says that you take the simplest theory, which is consistent with those other axioms. That last axiom, I never liked it very much. And it's a suitable candidate for the fifth axiom. That often people have sets of axioms. They have five, and the last one is the one that's questionable. So the simplicity axiom is questionable. And in the meantime, lots of people, including myself, have done work trying to get rid of that axiom or the simplicity axiom in other sets of axioms. So yeah, so that's that's the set of postulates. And I was motivated just simply by trying to get away from this abstract nature of quantum theory. I wasn't at the time, especially thinking about quantum gravity. However, one reason for doing this is, in fact, to think about quantum gravity, because when you start thinking about physical theories in these more general probabilistic ways, you're looking at a bigger set of possible theories and how to constrain down to a particular theory. And this is maybe a useful paradigm for thinking about quantum gravity as well.
Well, I've always been told that one of the key features of quantum theory is the quantization of, I guess, the states of objects. So, for instance, I guess take the energy levels of an electron uh, in like the orbitals of an atom, for example. That's the classic example that I'm always told in school. Uh, is there a way to get continuity in that example when the electron jumps up and down in energy level, or am I understanding this wrong?
Yeah. So in that system where you have an electron that can be in the ground state of the atom, sort of roughly speaking, that's the one closest to the center, or it can be in these higher excited states. And if it's in a higher excited state, it will typically it will very quickly go down to one of the lower states. Um, um, so and people often refer to that as a jump, as jumping from a higher state to a lower state. And it's not quite the same thing as what I was talking about, um, in the sense that the evolution really is continuous. To understand an atom properly, you'd also need to include um, some. You'd also need to include the electromagnetic field. You've got the photon that's released when the atom goes down to a lower state. And so really, you'd have to include some physical degrees of freedom corresponding to the photon that's emitted. And when you do all of that, and if you look now at what happens when you start off in the excited state, and then you end up in the ground state, so you de-excited. Really, what's happening is continuous. You'll start off in one state, and you go in a continuous way, evolving according to the Schrodinger equation until you end up in another state. So if you look at that properly, it's not actually a jump. It's a it's a continuous transformation. It's everything is consistent. It's not really jumping in some sense.
I see. And now that you bring up causality, you attempt to describe the universe without any direct reference to causality using something called the causaloid framework.
Okay.
Could you explain what this is and also how this ties into the issue of quantum gravity?
Okay. So um, so first of all, let me explain a particular problem with quantum gravity as I see it. So when people attack the problem of quantum gravity, usually they choose some particular problem and use that as a way of attacking it. Um, you might think about the fact that there's a minimum distance, the Planck length. A lot of people take that as the starting point for how to think about quantum gravity. We might choose some other feature. Um, for me, what seemed interesting was that there's this conceptual clash um, between quantum theory and general relativity with regard to how they treat causality. So in in general relativity, you have this thing called the metric, and the metric is what gives, as I said before, it's what gives you space and time. It's what gives you a measure. A metric is a measure on space and time in the vicinity of some point. Um, so what it really conveys is causality. Causality. It conveys what is before and what is after. If two points are, if one point is before or after another point, if one point is at the same time, called space-like separated from another point. So do two points have a time-like relationship with one another, or do they have a space-like relationship with one another? Um, so, so causality in general relativity is given by the metric, but the metric is something you have to solve for. So when you solve the equations of general relativity, you have to find out what the metric is equal to. It's not given to you in advance. It's a thing. It's a thing you have to solve. You have to find it, and it can be different in different physical situations. So this means that the causal structure, as conveyed by the metric, is dynamical, and that's a new feature. In previous physical theories, the causal structure was not dynamical. So this is a new feature in general relativity. And if you look at quantum theory, the causal structure also isn't dynamical. It has standard quantum theory has a background space-time, and then you have a background space-time and you evolve a state forward in time. General relativity doesn't have a fixed background space-time. So that's a big difference between the two theories. And in that respect, general relativity is radical and quantum theory is conservative. But you can look at the theories in another way, and then quantum theory is the one that's radical. So quantum theory has this property of indefiniteness. So a particle can be both here and here at the same time. If you ask where is the particle, well, the answer to that is indefinite. It's not in either place. It's in both places at the same time. You can have both things are true, and so this property of indefiniteness doesn't happen in general relativity. It's a property in quantum theory. So, and those properties seem in the dynamical causal structure in general relativity and the indefiniteness in quantum theory seem, in some sense, core to the very nature of those physical theories. That's what makes those physical theories interesting from a conceptual point of view. So then you might ask, well, what happens when those two things meet? So if you have indefiniteness and dynamical causal structure, then you're going to get indefinite causal structure. If those two things come together, then the causal structure itself will be indefinite. If you ask, is the causal structure this or that, the answer will be no, it's both. So you'll have both of them at the same time. And that sounds all well and good, but then how do you think about that? And it's hard because normally when we think about physical theories, we imagine we have some state at a given time, and then we evolve it forward in time. So the state at time zero, and then we evolve it according to some equations to later times. But if you have indefinite causal structure, then there isn't really any meaning to having a state at a given time. That concept stops making sense, because to have a state at a given time, you need to have definite causal structure. So then the challenge, as I saw it, was to find a framework, a mathematical framework, which could accommodate indefinite causal structure. And so that was why I built the causaloid framework. And I decided to start off in a very, very general way, in a very general operational way. And I imagined just that you had experimentalists and they were collecting data on cards. So they, every time they got some new piece of data, they would write it on a card. And then if they got another piece of data, they'd write that on a card as well. And at the end of the experiment, you'd have a big stack of cards collected from different places in this experiment during the course of this experiment. And then I imagine, well, all that information could be sent to a man who lives inside a box, and it's his job to see if he can make sense of the data that's on his cards. Can he find a predictive framework to make sense of that? And so I set up a mathematical framework that this guy inside the box could use to make probabilistic predictions concerning data collected in that way. And the key thing this was done in a way that didn't require the notion of a state evolving in time. So that was a crucial part of that endeavor. So that was the causaloid framework, and it was meant to be a framework that was that's hospitable to a theory of quantum gravity. In itself, it doesn't give you a theory of quantum gravity, but if you have the causaloid framework and then you have some additional principles, perhaps you could get to a theory of quantum gravity. That was the idea.